So hey guys, so in the previous session I stopped over here in measure of this question. So I'm going to continue from this here. So these are the steps to find out the IQ. So what you have to do is that order the data from least to greatest first. Okay, then find the median for that. Then the left side of the median is lower half, and the right side of the data is called upper half. So here is the box plot. Let me show. So first you order it and then find the median, and left side is called as lower half and right side is called as upper half. Okay, now calculate the median of both lower and upper half of the data called Q1 and Q3. So this you have to calculate uh, median for lower half and median for upper half. So you could see median for this is 25 and median for this upper half is 36. Okay. So next, what you have to do is that the IQR is the difference between the upper and the lower medians. So this is the IQR. Okay. This is the lower and this is the upper. Okay. So the difference between upper and the lower is lower half is called the IQR. Okay. So note when we write down minimum, maximum Q1, Q2, and Q3, this is called 5 point summary or five number summary. So let's solve some questions. So take a look at this data. So below are the weights of 5%. Calculate the mean and standard deviation. So what you do, calculate the mean for this, okay? And then after that, for standard deviation, you have the formula. So just substitute the value over here and you will get the mean and standard deviation. So now what they are saying is suppose each one of them is gained extra 5 kg weight during winters. Can you calculate the new mean and standard deviation? Yes. Okay, so what happens is that you have to add 5 kg to each of this value. When you add it, the mean will change, but the standard deviation won't change. I will show you that here. Mean and standard deviation. So this is what happens, okay? So what happens is that when you calculate this, when you calculate mean, it will change. Okay, from this position it will go to some other position, mean will change. But what happens is that when you add 5, when you're adding 5 kg extra to each value, the standard deviation won't get affected. Okay, you have to remember that the standard deviation won't get affected. It only get affected when you are multiplying or dividing the value with the weights. Okay, but if you are actually adding the weights for these weights that are already given, it's not going to change because it's at the end of the day, it's all about xi minus mu. Okay, so xi minus mu here, whatever extra phi you will get here, it will get subtracted. So at the end of the day, the standard deviation remains constant. If you are adding again, if the person is increasing, if all the data points are increased by a value of constant value. Now let's say consider the same set of people from previous example. Suppose that this person are advised to drink 2.5 ml of water for every kg they weigh plus 750 ml of water every day. So what happens is that in this case, I will show you this. Okay, so this is the question. Suppose that in order to stay hydrated, this student drink 2.5 ml of water for every pound they weigh, less 750 ml of water a day. What is the mean and standard deviation for the amount of water consumed every day? So we have got X bar to be 135.6 for the from the previous example. This mean value for this is 135.6. Okay. So what they are saying, consider the same set of previous people from previous example. Suppose these persons are advised to drink 2.5 ml. So 2.5 ml, and for every kg they want. So you may have to multiply 2.5, since for 1 kg it's 2.5. So since there are this much kg, so you have to multiply mean by 2.5. Okay, since you have taken the mean value from the previous, so you have to multiply by 2.5, and then they are saying that weigh plus 750 ml of water every day. So you have to add plus 750 over here. Okay. plus 750 ml of water every day. So mean value gets changed from x new, it becomes x 135.6 into 2.5 plus 750. It comes out to be 1089. Okay. So now what happens is what is the mean is calculated. Now standard deviation, to find the standard deviation, we have to take the previous example standard deviation over here. So it comes out to be 31.75. You can cross check. And as I said previously, standard deviation will just not change. Okay, standard deviation remains constant for addition. Okay, so you have to measure, understand this transforming data. Measure of center get affected by plus, minus, into, and division, and measure of spread is only affected by multiplication and division. So what happens? You have to multiply standard deviation by 2.5. Then only that is only going to get affected. So what happens? Let's take a curve like this. So if you are multiplying the standard deviation, it gets wider. Okay, you can see this standard deviation is 5, and to make it, you have to multiply by 2. This is how it works. Okay, it gets wider and wider if you multiply, and it gets thinner and thinner if you divide that. Okay. Now you have to understand measure of center is affected by multiplicative term and additive term, whereas measure of spread is affected only by multiplicative term, that is multiplication and division. Now let's come to measure of symmetry, or that is skewness and kurtosis. Okay? So skewness is usually described as measure of data symmetry, okay, or lack of symmetry. A perfectly symmetrical data set will have skewness of 0. Okay, the normal distribution has a skewness of 0. Okay, it's in normal distribution we don't have any skewness, and skewness is calculated using this. Okay, so let's write a code for this. So now it's skewness and kurtosis. So let's write a code for skewness. First import numpy. Next from scipy. So skewness and kurtosis are there in scientific Python library. So you have to import from scipy.stats. Import skewness. So we are doing skewness, right? So okay, import from import skew. Okay, it's skew. Okay, we have imported. So now let's take random value which is forming a normal distribution. Okay, let's take value between 0 and 2, and we have 10,000 values. So this I had to tell you. So this is about create random values based on normal distribution. Okay, so if you want to see this, so location is mean of the distribution. So what we are doing is that we are actually drawing a normal distribution where mean is 0 and the standard deviation comes out to be 2. Okay, so when the standard deviation is 2, you have to understand that standard deviation, the next standard deviation will be at the point 4. So for 99.73% of the data value which are present, it comes out to be around 8. Okay, 2, 2, 4, 4, 2, 6. Yeah, it comes out to be 6. Under minus 6 and 6, our data points will lie, all the data. So if you want, you can check it by passing x dot min or min of x. So minimum value is minus 7. As I said, the normal distribution, most of the points are concentrated within 99.73%, where 2 is a standard deviation and 2 into 3, 6. So most of the values are between minus 7, and most of the values will be between minus 6 and 6. Okay, and some points will be there which are outside our range. That is called known to be outlier. That is sometimes called known to be outliers. So now let's come to the normal part. So now if you want to see the skewness, so right here, print skew of x. So you could see the skewness comes out to be 0.02. Okay. So what I'm saying here is that uh, skewness is usually described as measure of data symmetry or lack of symmetry. A perfectly symmetrical data will have skewness of 0. Okay, so this is not perfect. As I said, the max comes out to be -7, which, or if it had been between -6 and 6, the skewness would have been 0. But yes, most of the time in real-time data, when you consider there are some outliers that are present within your data. So the skewness is still less. It's 0.02. Let's see how skewness works. So this is the formula for finding skewness, where n is the sample size, xi is the xi is the ith x value, and x bar is the average, and s is the sample standard deviation. Note that the exponent of summation it is 3. The skewness is referred to as third standardized central moment of probability model. So you can see, so when is the skewness too much? Okay, the rule of thumb says that if the skewness is between -0.5 and zero point 0.5, the data are fairly symmetrical. In our case, it's between -0.5 and zero point 0.5, which is 0.02, which is symmetrical. And between -0.5 is fairly symmetrical. And if the skewness is between -1 and -0.5, or between 0.5 and 1, the data is moderately skewed. And if the skewness is less than -1 or greater than 1, the data is highly skewed. If you want to see data which is highly skewed, let's pass instead of random, normal, let's pass random. Okay. So we are now actually trying to pass random value in the given shape. Okay. So let's see how it gets. So we have to pass an array random of 3 comma 2. We have to pass we have to pass number of rows and number of columns over here. So this is 3 rows, 2 columns. Mm, let's see. No, this doesn't work. Okay, it will be normal. So and also if you keep on running this code, it will change because random, right? So values will change. Sometimes it comes out, but it will be closer to 0. Okay, it will be closer to 0 always because it's a normal distribution curve. So now let's come to skew. First, so this is skewed to left. We say skewed to left when median is greater than the mean value, and we say skewed to right when mean is greater than median. So this is how. So mean is less than median, then it is skewed to the left. So median is over here and mean is over here, and median is greater than mean, then it's skewed to right. So if you see this box plot, there are values between 21 and 93, and you could see because of this value, it is skewed to left. Okay, all the values lies between 50 and 90, but because of this 21, it is fairly skewed to left. Okay, minimum, maximum is 93, and it comes out median is between maybe 63, and Q1 comes out to be 60, and Q3 comes out to be 80. So now what you do, let's remove this outlier from our data. And if you see now it's skewed to right, okay? Because it is actually the higher data points are actually having influence over our um, mean and median. Actually that higher data points are making sure that this value comes out to be a right skewed, okay? So in this case, if you see, skewed to right means mean is greater than median, and skewed to left is mean is less than median. So strategies for determining the skewness for a box plot. So what happens is that for equal boxes with the same whisker length, you will have symmetrical, and for unequal boxes, skewed to the right, and equal boxes, but it is skewed to the right if you see here, and unequal boxes, it is skewed to the left. You just have to understand from this series, if you see this equal boxes, that interquartile range is, you see Q1 median and median and Q1 and Q3 are at a equal distance. That is Q1 is equidistant from Q1 and Q3 are equidistant from median. But if you see the minimum and maximum value, you would see there is Qness that is there to the right, which is mean is there at the right side. Similarly, this is unequal boxes skewed to the left. Here, if you see the Q1 value is having a higher majority, so which is actually affecting the mean. So Q1 is left side, Q3 is right side, but the mean is less than the median over here. So when it comes to this, so now let's discuss about kurtosis. So kurtosis is all about the tails of the distribution, okay, not the peakness or flatness. It measures the tail heaviness. So for program for this is import numpy xmp, and from scientific Python we are importing kurtosis, and now creating random values based on normal. Now normal distribution. Now we print kurtosis. Okay. So let's copy the code from this. So instead, what we can do is that we just pass here instead of q, we pass kurtosis and import kurtosis over here. So you see the kurtosis comes out to be 0.112. Okay. So let's see more about kurtosis part. So when you see the kurtosis, you see where n is the sample size. So I want to see the more about kurtosis. Yeah. What does the kurtosis tells about the shape? Okay. Let's see. The reference standard of a norm is a normal distribution which has a kurtosis of 3. In token of this, often excess kurtosis is presented by excess kurtosis is equal to kurtosis constant. So we consider excess kurtosis to be our mean value where 0, the normal distribution having excess kurtosis exactly 0. Okay, normal distribution has excess kurtosis exactly 0. Any distribution with excess kurtosis 0 is called mesokurtic. So this is our mesokurtic curve. And a distribution with kurtosis, excess kurtosis less than 0 is called platykurtic. Compared to normal distribution, its tail are shorter and thinner, and often its central peak is lower and broader. This is platykurtic, where tails are shorter and thinner, and often its peak is lower and broader. The distribution with excess kurtosis greater than 0 is called leptokurtic. Compared to normal distribution, its tails are longer and flatter, and often its central peak is higher and sharp. Usually, what you have to consider is we don't consider kurtosis, we always consider excess kurtosis, so that our excess kurtosis value exactly lies in 0. So, if you see the kurtosis part over here, so this is how it looks, okay? So this is platykurtic and mesokurtic and leptokurtic. If you see the leptokurtic is more dense compared to mesokurtic, and the mesokurtic is more dense compared to platykurtic. And in our case, platykurtic means where excess kurtosis is less than 0. Platykurtic means excess kurtosis less than 0, and leptokurtic is excess kurtosis greater than 0. And mesokurtic is where it follows normal distribution with excess kurtosis is equal to 0. So in our case, the code we wrote, the kurtosis comes out to be 0.11. You can say it's greater than 0, right? It's greater than 0. Excess we consider excess kurtosis. So our curve is supposed to be leptokurtic. So if you run this again, if you run this and this, it comes out to 0.06. So it's almost a mesokurtic curve. Okay, it's almost not completely, but It's but still you can say it's a leptopatic curve if you want. Now let's come to the next part of our class, so which is uses of kurtosis. Okay, kurtosis depicts the shape of distribution, especially tails. As I said, it tells the shape of distribution, especially tails. Okay, outlier detection, large kurtosis suggests there could be outliers in our data. Okay, excess kurtosis should be as close to zero, because if it is more than greater than zero and if its value is higher, then there could be outliers in our data. With high kurtosis, there is chance of high variance. Yes, high kurtosis leads to high variance, and hence test on mean could lead to bad results. As I said, with outliers, there is a chance of high variance, and because of that, test on mean could be bad, because outliers will affect the mean value. So in that case, we will choose median, test on median. Okay. Hence, in that case, we will need to choose a most robust option like test on median. So financial risk is the return of your asset can be farther from the mean than predicted using normal distribution. That's what I'm saying. If you have outliers in your data, then median you should be considering, not the mean value. Okay, because mean is going to give some bad result with the presence of high outliers. So let's come to outliers. What is outlier? So I will now tell you. So outlier is an observation that lies an abnormal distance from other values in a random sample from a population. Okay? In a sense, this definition leaves it up to analysts to decide what will be considered abnormal. So see, if you see this chart over here or graph, you see all the data points are concentrated like it's like a linear kind of curve. Okay, it's not very linear, but still you can see there is some kind of pattern. Okay, as x values are increasing, y values are also increasing. But if you see, there is an abnormality over here. At this point, all the values are between this point and this point, but it comes out there is one point which lies over here, and here also all the points are over here, it is comes out to be here. So there are abnormals in our data which you can see. So this is called as an outlier. Okay, common causes of outliers can be data entry errors, like human errors, like let's say you are actually supposed to mark the age of a person. You have to enter the age of a person, and by mistake, instead of marking a a child with 12 years, you marked it as 120 years. Okay, so there is an outlier. Okay, that kind of error can happen. Human error can happen. Like instead of 24 years, if you write to 40, so that is not possible, right? So that kind of data will affect our results. Okay, for the experiment that we are conducting. So now let's come to measurement errors, instrument errors. There can be instrument errors, like consider in some of the experiments that you do, like in physics, if you had done vernier calipers kind of thing, there can be experiment errors, so sperometer, vernier calipers kind of thing. So yes, there are experiment errors where that can be due to the instrument. So now some are sorry, this is measurement errors. Okay, some are the second one, which is measurement error, which is instrument errors. Now let's come to experiment errors. Experiment error is like data extraction or experiment planning execution errors. Like while checking the value, you made a mistake. While reading the value, you read it wrongly instead of uh, whichever value you should have read. So now sometimes you are intentionally making the outlier so that dummy outliers made to test detection methods. So if you are knowingly doing that, so that if you could see what kind of result you will get for that intentional errors. So data processing errors can be there sometimes by data manipulation, data set unintended imitation. There are sampling errors also. There are natural errors also, not caused by human or any instrument. It is natural. Okay. Common methods to determine an outlier. Okay. So what are the common methods to determine an outlier? So what you can do is that you can sort the data and see the extreme values first, then plot the box plot and scatter plot. IQR method also you can do, or using Z-score method also you can find. If you see the graph here, because of these outliers that are present in here, it's actually affecting the other predictions as well. So if you predict from this line that we have got linear line, that we have that linear regression we have calculated, because of this points our data is getting affected. So what we have to do, we have to take care of these outliers by doing some manipulation on the data and make sure that we have to record once again the observation based on this data. So you can do like you can filter it out, or you can scale down these values in such a way that whatever I'm using IQR, you can do that. So let me show you. Now, why do we need to treat outliers? Outlier can impact the result of our analysis. As statistical modeling. Okay, so let's see how we can deal with outlier. So this part is finding outlier. So we are going to find outlier using IQR method. So we have to import numpy as MP. We have already imported that. So, so let's take a data value, data points. Okay. Let me take some data points, 2, 2, 3, 1, 2, 2, 2, 3, minus 18, comma 1, comma 1, comma 2. So we have taken some data points. So I'm going to write a function first. Let me write a function called outlier detection. Let me pass. So I have to pass a variable over here. Variable is our data, okay, that we have taken over here. So we can find out Q1 comma Q3 using np dot percentile of variable comma what you want in percentile. So we have various attributes over here. We want I can AQ input array or object that can be converted to an array. So we are passing variable as our input array and array percentile of sequence q of particular to compute, which must be between 0 and 1. So I'm passing the values over here 25 comma 75. So I want the 25th percentile and 75th percentile, which is our Q1 and Q3 respectively. So we want to find the IQR now. IQR is Q3 minus Q1. So this is our IQR. So lower bound will find lower bound. Lower bound is Q1 minus 0.5 into IQR, and upper bound comes out to be Q3 plus 0.5 times IQR. Okay. So now, so what we want to do? So we want to detect the outliers, right? So output is equal to, so we will take variable or variable in variable if, what's the condition we have to give? If where is greater than lower bound, or, okay, I have to use or function now, or if, so or we have to pass only if, or variable is greater than variable is less than lower bound, or if it is variable is greater than upper bound, then we will take that out as output in our output, okay, list, in our output list. Let me return this output, return out. So now let me pass outlier detection of data. So let's see what's the value of it. So you can see that from our data, this 15 and minus 18 comes out to be our outlier, okay? So this is how you can find outlier using IQR method. So this is IQR method. A data value is considered to be an outlier if data value is less than microgram minus 1.5 QR. Or this 1.5 QR we are taking. We can take any value like 2.5 IQR as well, but usually we consider this to be 1.5. But yes, this can vary based on the uh, kind of data set we are dealing with. Okay. So now data value is greater than Q3 plus 1.5 QR, then it's outlier. So now, can you identify the outliers from the below data set using the IQR method? You can see here, I would like you to solve this data set by your own. The outlier here is minus 350 degrees Celsius because all the values lie between around 15 to 30 degrees Celsius, 31 degrees Celsius. But this is only one value which is actually affecting our data, that is minus 350. You will actually calculate this. You can calculate this. I hope you can do it on your own. Now let's take a 5 number summary. So you have a data set where a value lies between 10 and 51. Let's see the outliers that are present. So Q1 is comes out to be 21 minus 1.5 into IQR, that is 36 minus 25 is 11. So it comes up to be 28.5. So value less than 8.5 is considered to be your outlier. And now my upper value is, yeah, 36 is our Q3. Q3 plus 1.5 here is 11, so 52.5. So you can see that upper bound is 52.5 and the lower bound is 8.5. So 8.5 is 10 is greater than 10, 8.5, so it's fine over here. But here 59 is greater than 52.5, which is not a good thing since there is an outlier present in our data set. So we have to remove this point. Hence, we can say that 59 is the only outlier in our data set. So now the mu maximum, whichever is there, it's going to come out to be 52, 50, okay, when you remove this point from your data set. So now we have Z-score method. So Z-score can quantify the unusualness of an observation when your data follows the normal distribution. Z-scores are normally the standard deviation above and below the mean that each value falls assuming a normal distribution. For example, a z-score of 2 indicates that an observation is, while z-score of minus 2 indicates it is the standard deviation. Okay. So let's see this. So point to understand. The further away an observation z-score is from 0, the more unusual it is. A standard cutoff value for finding outliers has z-score of plus or minus 3 or further from 0. In a population that follows the normal distribution, z-score values more than extreme than plus or minus 3 have probability of around 0.27, which is about 1 in 370 observation. Okay. So let's consider a data set, find out the outlier using z-score method. So let's do this in our Jupyter notebook. So z-score method. So now let's take the data. Data is already, let me take the data that is present over here. It's 1, comma 2, comma 2, comma 2, comma 3, comma 1, comma 1, comma minus, what is this next value? 15, comma 2, comma 2, comma 2, comma 3, comma 1, comma 1, comma. So this is the value. So mean comes out to be 2.6. Let's check it. np dot mean of data. Okay, so 2.67 is our mean. And let's find out the Z score for each. So let's see which is the outlier. So here you see Z of 1 is minus 0.49 and Z of 2 is minus 0.19 and Z of 3 is 0.109, but Z of 15 is 3.67, which is out of range of minus 3 and 3. Okay, we will turn the point outlier if it has a Z score of 3 or above in any side, positive or negative. Hence, there is an outlier of minus 15. Let's try to check it. Okay. So, let's find the standard deviation consortium np.std of data. So we have mean, mean is equal to this much and standard deviation is equal to this much. So let's take threshold as 3. So let's take a outlier. So instead taking outlier, let's take an outlier list is equal to empty list. So for I in data, so how we can find out Z score using x minus mu by sigma. If I minus mean by std is greater than 3, let's take in the, so um, let's take z value first. Z is equal to, this is control x, control v, control v, control z, control z, control x, control v. Okay. I minus mean by standard deviation. So if z is greater than 3 or z is greater than, z is less than minus 3, then outlier dot append of I, print outlier. We could see that in our data 15 comes out to be outlier, and here also there is an outlier at 15. Okay, so this is all about finding outlier using z-score. Now let's come to covariance. So you have to understand that covariance gives us direction, the positive or the negative direction, that is known to be covariance. So if for x values, if there is, if for x increase in x there is increase in y, then that is known to be positive variance, and if it is for increase in x there is a decrease in y, then that is considered to be negative covariance. So covariance is used to find the direction, how it is how data x is related with y, if it is positively or negatively related. So this gives, if x with increase in x, if y is increasing, then we will get a positive slope, and with increase in x, we get decreasing y, we'll get a negative slope. So covariance, you just have to understand that it gives the direction. It gives the direction. Whereas now we have come to correlation. So for covariance, you have to understand that. So we have seen variance, right? So variance is nothing but the univariate analysis, whereas covariance is a bivariate analysis. So in covariance, we replace x minus x bar whole square by x minus x bar into x minus x bar. Okay, let me go back to the covariance part. So we have x minus x bar whole square, right? So since there are, for bivariate we have two variables, so we have to replace x minus x bar whole square by x minus x bar into x minus x bar. Then we have to replace x minus x bar, 1 x minus x bar by y minus y bar, since there are we are looking for a bivariate analysis, and n minus 1 is for the samples. Okay, so this is covariance of x comma y, that is summation I goes from 1 to n xi minus x bar into y minus y bar by n minus 1. Okay, in Python we use function for covariance, and correlation is covariance by standard deviation of x into standard deviation of y. So what is correlation? So this is one of the important concepts in while performing statistics, and also it will help you to say how data are correlated. So correlation is a statistic technique to depict relations between two variables, strength and direction. So strength is calculated by the positive or negative sign, and sorry, strength is calculated by the magnitude, which lies between -1 and 1 for correlation coefficient, and direction will be negative or positive. That is how it is correlated, that is positively or negatively. So we measure the correlation with the help of correlation coefficient. For example, height and weight are related. Taller people tend to be more heavier than the shorter people. What is correlation coefficient? The Pearson's correlation coefficient is measured that determines the degree of which the moment of two variables is associated. The value of correlation coefficient lies between -1 and 1. So formula for Pearson's correlation coefficient is data frame dot correlation method is equal to Pearson. Okay. So let me first take this. This is a formula for finding correlation coefficient. You can see that the formula is similar to covariance. You just have to divide by standard deviation of x into standard deviation of y in the denominator. So n is sample size, Sx and x are standard deviation of samples x and y. X bar, V bar are mean of x and y samples, where x and y are the sample points of x and y respectively. So positive and negative correlation. Correlation coefficient greater than 0 indicates a positive correlation. This is positive correlation. With a value less than 0 indicates a negative correlation. And the value 0 indicates there is no relation between the two variables being compared. Strong and weak correlation. Kind of correlation depicts sign of correlation coefficient. So if you see, this is a strong correlation because the linear curve we have, the linear line we have, actually almost gives the true value for our data set. I mean, it is almost precise comparison to the data points that are available within our data set. And we have seen that correlation is 0.9. That means x is strongly related with y. That is value x and y are highly correlated. So if you see this weak correlation with 0.6, you see some values are having away from the linear line, far away from linear line. So that's why some points are on the line and some points are near to the linear line. So this is weak correlation because of some points are far away and it is giving high covariance. And now we can see there is no correlation here. You can't draw a linear line that covers most of the points in our data set. So this is no correlation. This is negative correlation. It is in negative slope it is having, and this is weak negative correlation which is having a few data points that is passing through and its slope is negative. So if you see direction correlation gives direction and strength. R has value between 1 and -1. Okay, correlation which have correlation coefficient has 1 and -1 between those values. The strength of the linear relationship increased as R got close to 1 or -1. Okay. So now if you see R is -1 means highly correlated in the negative direction, and R is equal to 1 means highly correlated in the positive direction, and R equal to 0 is there is no correlation. And these are somewhat, this is bit strong correlation, and these are weak correlation 0.4 and -0.4. And this is also bit strong correlation. But a rule of thumb is any relationship with a magnitude of R greater than 0.75 can be considered to be a strong correlation. So -0.84 is a strong negative correlation, 0.90 is a strong positive correlation. So a teacher wants to determine the correlation between the number of hours spent studying and test scores. So these are the study student name, and this is we have to find the correlation between the number of hours spent studying and test score. This is the test score, and this is the hour studied by students. So we have to find the relay correlation between that. So if you see, we have calculated xi, we have our xi and yi. So we have calculated our xi minus x bar. X bar comes out to be 12.5 mean, and y bar comes out to be 68 marks. And if you see, we have calculated the difference, and we have multiplied the difference, and we have summed the value. It comes out to be 821. We have to substitute 821 divided by 5, 6 minus 1. Number of samples is total 3, 6 values, and 6 minus 5. And standard deviation of x comes out to be 8.28 and 32.29 for x, standard deviation of 5. So substitute those values in this and check what is the result. Similarly, I would like you to make sure that you solve this question. I would like to make sure that you solve this question by yourself. Take this data, take temperature as one area x-ray and ice cream sales as y, and do the correlation coefficient and check how what is the correlation. Do the correlation, check what is the correlation coefficient, and check the nature and strength of the correlation. So we have seen till now the Pearson's correlation coefficient, which is lies between minus 1 and 1, and we have Spearman rank correlation. This is only used for non-linear variable. You must understand this is only used for non-linear variables only. In Python, we have data frame dot correlation of method of Spearman. Okay, so we have to pass method to be Spearman for a non-linear variables. So here the coefficient is 1 minus 6 into summation of difference square by n of number of samples divided by n square minus 1. I will show you using an example. Steps for Spearman correlation coefficient. So create a new column for rank of x. Okay. So we see this problem. Okay. The scores of 10 students in English and Maths are follows. So this is English marks and Maths marks. So first you have to give the rank of x and assign the rank of each variable. So assign rank for each variable. For x, my English and rank of max. Okay. So you see 75, which is rank 1, 80 is highest, and rank 10 is 45 is the lowest. So rank for English and max accordingly, and take the difference between rank of English and rank of max, and whatever difference you get, square the difference. Okay, you square the difference, and then using this formula you sum it up, sum the difference up, after squaring, so it comes out to be 754. Now here number of samples to be how much? 10. So 10 minus 10 into 10 square minus 1. So this comes out to be zero point 0.6 as the Spearman rank coefficient. Okay. So points to ponder. So correlation. A few years ago, a survey of employees found a strong positive correlation between studying an external course and sick leave days. Does this mean studying makes them sick? People study a lot, or did they lie about sick so they can study more? Without further research, we can't be sure why and what is the reason for studying an external course leads to sick leave days. This is you just can't make an assumption that studying makes them sick, right? So you have to find a relation. What is the main reason for studying how studying an external course and sick leave days are related? Similarly, the poor suburbs are more likely to have high population. So we have to find a relation if poor suburbs have high population, and then only what is the likelihood of that, we have to check that. So we have to now we have come to the end of the descriptive statistics. So before completing this part, I would like to write the code for uh, covariance and finding covariance and correlation coefficient. So covariance. So for the Python function for covariance is nothing but np.co, but we have to pass here x and y because we are looking for bivariate analysis. So x comma y. So let me take x value and y value. So x is equal to, let me take some data point, 1.23, 2.12, 2.12, 3.34, 4. This is my x variable, and this, let me take y variable as well. 2.56, 2.89, 3.76, and 3.95. So you see the covariance of x comma y comes out to be a matrix order. This is our covariance of x comma y. So let's find the correlation coefficient. Correlation coefficient. Let's do both Pearson and Spear. So let for Pearson and Spearman, in scientific Python.stats, we have a function called Spearman. Pearson, we have to take that. First, let me take put scipy.stats from scipy.stats, and say import Pearson from Spearman. That is, this is Pearson R, and this is Spearman R. So let's take x variable and let's take an array p dot here p dot a, p dot array of, let's take values 10, 20, 30, 80, 34, 24, 12, 18, 98, 1 by is np dot array of 2, 1, 4, 5, 8, 12, 25, 96. Print Pearson R of x comma y and Spearman of x comma y. What's the check? X and y must have the same length. So there is some mismatch in length, I guess. 2, 5, 12, 18, 25, 96, 48. How many points are there? 1, 2, 3, 4, 5, 6, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. There is a value is 8 here. So we could see that the Pearson result we got is 0.69. So we have to, for Pearson, we have to take 0th index, and as well as Spearman, we have to 0th index for getting our correlation coefficient. So the correlation coefficient comes out to be 0.69 and 0.69 in our case. So we don't have an example related to that, I guess. Okay. And the correlation coefficient for Spearman comes out to be 0.442. So this is all about the descriptive statistics. Let me recap it. So we have seen in the first sessions, and we have seen statistics and its importance, population as a sample, types of variables like quantitative, categorical, ordinal, nominal, and discrete continuous. We have also seen types of chart like pie chart, line chart, scatter plot, histogram, bar chart, and box plot. We have also seen descriptive stats like measure of central tendency, measure of spread, and measure of symmetry. We have seen five number summary, effective transmission of central tendency and spread. Also, we have seen outliers and modified box plot and how to detect. We have also seen covariance, correlation, Pearson's correlation, coefficient, nature, and strength of correlation, how to calculate Pearson's correlation and Spearman's rank correlation coefficient. Thank you for attending the session. I will be continuing with the statistics for data science lectures in the coming videos, where I will be covering probability distribution and also sampling techniques, sampling. So thanks for attending the session. Bye.